So one thing is that your test for this chapter is going to be on Friday next week. Okay, so kind of know that. I did make an ELF time review for it, but it's on Tuesday, because Thursday I have to have one for geometry. So Tuesday next week is some limits review for the test. And then we'll also have like another review assignment. So today on the right-hand side, actually 114 got on here by accident. We're doing these 4 skills. Some of it's going to be familiar from your pre-calculus stuff. So part of it's really easy, and then part of it, the notation's just so you get bogged down in writing it out. But overall, not a too difficult concept. So we're going to be working with what makes functions continuous and how to explain when and why they fail to be continuous. So basically, continuity loosely is there's no interruptions in the graph. So you can trace it with your pencil or your finger, and you never have to lift your pencil. So if you can see the graph, continuity at a point is super easy, because you just look and say, do I lift my pencil? And sometimes they'll say, is the entire graph continuous? Sometimes it says just at a single point. And so for all of these, we're going to talk about the continuity at the specific value of c. So these up here are 4 graphs where the function is not continuous at c. So we basically travel, and do we have to lift our pencil? Yes. This function is not continuous, because to be continuous, f of c must be defined. Basically what that means is there is not an open dot there or a hole there. So this guy right here, discontinuous, if you had to say why, you'd say f of c either doesn't exist or isn't defined. You go with that one? This one at f c, the function does exist or is defined there, right? But what's causing its discontinuity is the limit approach from both sides. So the other thing that has to happen is that the limit as you approach that value from the left of the function has to match up or be equal to or at the same height as the limit as you approach from the right on that function. So there's 2 criteria up here right now. And then we'll have a third. So when you're asked to use the 3-part definition of continuity, these are the 3 parts that must be true for the function to be continuous. So again, the first graph fails number 1. F of c is not defined. The limit exists, right? You're at the same spot or the same height. If this was a 3, you'd say, well, the limit is 3. The limit exists, but the function value doesn't. This one's the reverse. The function value exists right here, but the limit doesn't. The third graph right here passes criteria number 1. F of c exists. It's right down there. I see a solid dot. The limit exists. It's up here. But again, the function's not continuous. So there's 3 pieces. Do you see why there's got to be 3? Because there's 3 situations up here. So our last one is that the limit, as you approach that value, which in this case is c, from both directions, has to actually be equal to. So that dot would have had to have been defined up there. So we say it has to be equal to where the solid dot is. So loosely, there's got to be a closed dot, and your limit has to be at that closed dot. So that would make a function continuous. This guy right here actually fails the first 2 and the third, so it fails all 3 of them, right? So that's kind of a unique case. When you have an asymptote, it's a hot mess is really what happens. So on the next page, we're going to launch right into an actual AP FRQ. It's from 2011. It was their last question. There's 6 of them, so it's part of the last question. I can't ask you the other parts because they involve other things you haven't learned yet, like integrals and derivatives. But there was a continuity question, just so you can see how you'll be tested on it on my test, because I try to mimic AP. So you'll be in the first test, kind of is going to throw you for a loop, because if you get, like, say 70%, it might still, through calculation, be like 86. Does that make sense? I scale it towards AP. So, and it's at, but you're tested at that level as well. So are they going to be difficult? Yes. But in AP, 50% right is a 3. Like if you get half of the AP exam correct, you will earn a 3. What grade do you think sort of corresponds to a 3? A C. So you're going to get your test back and you'll go, oh, look what I got wrong. And then there's going to be some conversions. So, which is good and bad because they're hard tests, but they convert. So it's kind of nice. But anyway, if I had one like this on here, I'd be looking for 3 things because it says to show, so circle that word. It doesn't say is the function continuous or determine if it is. It says show that it is. So they're telling me this function is continuous. You need to show me the math. Do you think you'd have a calculator? No. So you can't go graph it. You have to mathematically show that 3 criteria are met. I just told you them. The first one was that I have to make sure that the function exists at 0. So I just have to go on there. Basically, if I don't see this line under here, it fails the first one. So there's rarely will it fail the first test because it's too easy. But on Delta Math tomorrow for your assignment, there's a couple where you're just going to click on not continuous because you're going to do it, but it's not defined there. So don't forget to look for it. But we're going to say f of 0. We're going to say what it equals. It's 1 minus 2 sine 0 because that's where the inclusion bar is. Sine 0 is 0. So this is just 1. So what I'm going to do is tell my grader that, and this symbol right here, a triangle formed from 3 dots. Do any of you guys know what that's the symbol for? It's universal, so it's not just me. Anyone in math, high levels of math would know you're telling me therefore. You're drawing the conclusion. So that means therefore. All right? So I'm going to say therefore, f of 0 is defined. So easy math, but you have to know how to write it. I told you we do a graphical, numerical, algebraic, or analytical, and written word. This would fall under the W. How do you write your answer? All right, number 2. Now that I've showed that there's a solid dot there, I have to make sure that my limit exists. So the second thing is, this is solid dot, this is that there's a limit. So I'm going to say the limit as x approaches 0 from the left of the function. I already found it up there because that was this part. So I'm just going to write equals 1. I already calculated it. Then what do you think I'm going to come in from? Right. Yep, I have to write it out. So like I said, somebody asked me if it's hard to do. I'm like, well, the concept's easy. The writing of it gets a little cumbersome. There's nothing I can do about that, though. It just is the way it is. So as I come in from the right, I'd use this piece, and I do e to the negative 4 times 0, which is also 1. It better have been, because it said to show it is. So basically, all 3 of these numbers have to match. You're nodding, right? Watch this. Had that been a 4, I would have been up at 1, but the function was defined up there. Discontinuity. Does that make sense? So they all have to match. So the last thing I have to show for number 3 basically is that everything's in alignment. My limit, as I approach 0 from both directions, so I won't put anything on there, of the function was actually equal to the value there. That's what I'm saying. My approach is where the dot is. You can't write that though. Right? You can't write it. Your approach from the left and right is where the dot is. You have to write it in math speak. You could even write equals 1 if you want, because that's true. All right, I'm done. How many points would I have earned for that one? 3. It was worth 3 points that year for the 3 parts. Now, if you just went like this, okay, if you went like that and went 1, went like that and went 1, and went 1 equals 1, yes. How many points do you think something like that would earn you? 0. Does everybody in this world know that 1 equals 1? Okay, what are you telling me? Right? And drawing an arrow, I don't know what you're telling me, right? You have to say you're taking a limit. So the writing's kind of messy. Anyway, the next part of it is what kind of discontinuities you have. And you should have learned that there are both non-removable, which means basically, I'm going to tell you what I think of with non-removable and the other one, removable. Those are familiar from pre-calc, right, guys? Those words? All right. So, removable is basically you can define or redefine 1 point and fix the issue. How many points? 1. You can make one singular statement, and it will fix the issue and let you drive over the bridge. Like it'll fix the hole in the bridge. All right? So my non-removable, I'm just going to put NR. What happens on the graph for non-removable is one or the other of two things. Which two words up here do you think would give you a non-removable discontinuity? Go ahead and read through that word bank. There's two of those situations where you're going to write non-removable. I cannot fix it. You got one for me? What? Go ahead. Asymptote. Yeah. Sometimes some college text or the book we used to use when I taught out of a book would call an asymptote a non-removable infinite discontinuity to give that asymptotic like flavor to the statement. What other one up here besides asymptote is a type of situation that you cannot fix it? Joe, I heard it. Yep. So if you're listening to the video, those of you who told me to record this because you're going to be absent, it's called a non-removable jump discontinuity. That graphically looks like this. I cannot redefine just one point, right? She might say, well, I want that dot to be here. Well, that just opens this one up, but you still have an infinite amount more that are a problem. You can only redefine one point. So when we go down here, and we talk about this graph right here, it says determine all x values where f of x is not continuous. So first of all, I'm just going to travel the graph. Anywhere I have to lift my pencil, I'm going to write it down. So I'm heading out to lift my pencil. So I'm going to say at x equals -1. Then I'm going to travel. I'm in asymptote. I have to lift my pencil. So at x equals 1. But I lifted and came back down. Whoop, got to lift my pencil at x equals 3. So visually, and then I'd have to lift my pencil again at x equals 5. So visually, super easy to spot discontinuities. It's just anywhere when you travel, it disrupts it. All right? Then it says, classify each as removable or non-removable. So let's go to my first one. What kind is that? It's a jump. Can I fix it with 1 point? No. So I'd say non-removable. And it's actually, I like it if you put the word jump on there because there's two kinds of non-removable. So I'm going to write non-removable jump, and I'm not going to write discontinuity. At x equals 1, removable or non-removable? Non. I can't fix it with just 1 point. So non-removable, but what do you think I would call it? Asymptotic, or some books call it infinite, to say, well, you're going to the infinities, you cannot just plop a point in and fix it. So that would be a non-removable infinite discontinuity. How about here at 3? Removable or non-removable? Removable. And if I told not Cole to remove it, he would just say one statement. He would say f of 3 equals 0. That's my one statement, my 1 point I'm going to redeclare, right? And that would be like plugging that one. So that one's removable. How about at x equals 5? Removable or non-removable? Removable. I can make one statement. F of 5, u equal 2. Pluggable. All right? So easy when it's graphical. So when you get to I'm trying to turn the page and it's too close to that pause button. All right, so when we get to the ones where the graph has been removed, you kind of have to have your poop in the group a little bit better. You really need to, in your brain, sort of know what the graph would look like without being able to graph it. So this has a function g of x. It's polynomially, and it says find the x values where g of x is not continuous. I want you to put this in a box. Because when it's algebra and it says not continuous, generally, almost always, 99% of the time, the issues are with the denominator. And if you don't see a denominator, almost always, it means the function's continuous everywhere. I said almost always, right? But it's a good rule of thumb to say I need to analyze that denominator. So what I'm going to do is see all of its pieces. So I'm going to factor the top to see what I've got going. There we go. How are we doing now? You guys, I usually interact with you more. Are we good? Am I going too fast? No? Okay, great. We're I record, I don't get as good of a vibe, but I do like it this quiet. So there we go. So I have now factored it. I'm going to look in my denominator to find my discontinuities. My denominator has two issues, which means I've got two problems with the graph, and they are at x equals 5 and at x equals -2, because we cannot divide by 0. So I've got problematic behavior at those two places. It says classify each type of discontinuity. Well, I can remove this problem, aka cancels, right? So at x equals 5, I would say it is a removable discontinuity. I could plug the hole, right? So I'm going to write removable. And then if I ask you to remove it, that's a higher level question. If I said redefine one point, which means the issue was at 5, right? There's a hole in the graph. But if I made one statement, f of 5 equals 13/7, right? Don't do this. But if I went down here and made one statement, and f of 5 equals 13/7, I have now just with one singular point made it continuous. Did that sink? All right? Take that out, though. That wasn't part of the question. That's like just digging deeper. At x equals -2, it did not cancel. I can't remove the problem, right? Do you remember what kind of a problem that is when a denominator does not cancel? It's an asymptote, a vertical asymptote, which we can't remove, so we would write non-removable. I'm just going to write non-R. If I ask you to be more specific, or if it's multiple choice, you'd pick non-removable infinite discontinuity, because there's a vertical asymptote there. All right? The last two. Any questions on that one, though, just because I am just talking it through? All right. This last one is a pretty robust 4-part piecewise function. In my head, I kind of want to make sure what's happening. To the left of 2 at -10, I'm in on a line. It's going up 2 over 1, up 2 over 1, up 2 over 1. But when I get to -2, open, stop. You're not correct? Then I transition at -2. So I want you to circle these transitions. At -2, I transition to a parabola, correct? So all of these are continuous on their domains, lines, parabolas, and lines. They don't have any asymptotes and holes. They're all great. I just have to make sure they seal up greatly. You're nodding? Okay. So really, if I had to show my work here, I would ask myself, does h of -2 exist? Yes or no? There's one really easy thing to look at. Just make sure there's a 5 there. So I'm just going to write h of 2 exists. I'm not going to say which it is. So we're good. So far I know that there is a solid dot at the transition. But now I have to make sure that that solid dot, I don't have that kind of a transition. Yes? So what do? I take a limit. I go like this. I have to come in and approach my boundary from the left on h, see how high it is, aka stuff it in. But if over here you just go, oh, -5, and over here another -5, you won't get full credit. You have to launch into existence the limits. All right? So my limit as I come in from the left is -5. Now I'm going to test from the right. 4 minus is also, so I think I'll just link this as like a compound equality. I'm going to take my limit as x approaches -2 from the right of h of x. I am telling you that that is a nice, perfect seal. So I'm going to grab this and move it right there. That's what I just confirmed. Did you see what I just did? Because I did it fast. So I'm going to go back. I wasn't sure whether I had that issue going, but once I found they were both up at 5, I know that at 5 on my y-axis, both of those are there. So it says, determine all values where h of x is discontinuous. I'm good at the first transition. Okay? I'm just going to write c at x equals -2. I was continuous there, perfect seal. Now see if you can anticipate, because you can see I don't have a ton of examples. I do a couple, you have to really listen. Do you prefer that? Or do you sometimes say, I wish you did more examples? I don't know. You can go either way. Okay. So, what am I going to check next? Now I'm riding along that parabola until I hit what number? 1 on the x-axis. Then I transition into a line again. First thing I have to make sure is that there's a solid dot there. Is there? Yes, you're nodding, right? So h of 1 exists. It actually equals -8. If you want to write that, that's telling me it exists. But you're basically going, yep, I got a solid dot there. Then I have to check, correct, that at this next transition, not only again is there a solid dot, but they meet up. So again, it's a limit question. Is the limit as x approaches, what would be 1, right? 1 from the left on the function. Let's go evaluate that. I just said what it was, -8, right? That actually is matching where the dot is. So far, I'm good, right? So then I'm going to come in from the right. Limit x approach. You can tell I've been writing one go on today. I told you when I write it a lot in one day, it ends up like that. So, just so you know. As I approach -1 from that was from the left, and it's supposed to be +1, sorry. I'm approaching +1 from the right. So I'm going to go plug it in, and I'm up at 5. You should know immediately what that graph looks like. Do you? You can't see it, but at 1, there is a dot. It's where the parabola ended, correct? And that dot is at -8. Agreed? But at 1, the line takes off from a height of 5. Agreed? So let's classify it. There is a discontinuity. What kind is it? Non-removable jump. Awesome, you guys. So I'm going to write non-removable jump. Technically, I should write discontinuity at x equals 1 if it was a full FRQ, but this isn't. So we'll practice that next week when we get closer to the test. By the way, your test will look similar to an AP exam. You'll have multiple choice, some calculator, some not, and you'll have 2 FRQs, 1 calculator, 1 not. Make sense? Yes. Continuous. Yes. This one's continuous, so I didn't have to classify a discontinuity. This one's not continuous, so I classified it. I'm sorry, I'm abbreviating, and I probably shouldn't, but I can't help it. Alright, so the next one, don't forget to check the first thing. What was the first thing I checked on the other 2 transitions? That there was a closed dot, right? Is there on this one at 3? All you have to write is h of 3 is undefined. But to classify it, I need more work, because I have to decide this. Did those lines go like that, in which case it's removable, right? Or did those lines maybe go like that, in which case it's non-removable? So what do I kind of still need to verify? Where I am. So I still need to take a limit. Let's go just look at that. When I put in a 3, how high up will I be on line number 1? 11, right? When I put in a 3, what's my height on line number 2? 11. They're at the same height. Agreed? So that helps me classify it. Basically, I'd have to write a limit statement. Let's do it really quick. Limit as x approaches 3. Let's kill it off with one statement. From both directions was equal to 11. That's legal, by the way. If they're equal, you can show it as one statement. If they're not, you kind of need to show it as 2. So this one over here, I could have left off that, and then taken that off. I'm telling you they're the same. All right? So now I'm going to define it. Removable or non-removable? Removable, right? This is a removable. Situationally, it's this kind. What that? I had a slope of 3, and then the next one was steeper, so it's kind of like that. So I'm going to write removable. I'll write it a little better. Removable discontinuity asked you to remove it. What if I added another layer to this question? Make one statement. So add a fifth piece to this piecewise function where you make one statement about the point where now that becomes continuous. What do you think I say? H of x equals what? 11, right? When? Cool, right? That would remove it. But I didn't ask that, so don't write that in your notes. I didn't add it, but I'm adding I like to tell you, I make you practice a little harder than you play, right? We dug a little deeper into that question. Our last one. All right. Very high level question. Here we go. Are you ready? Ready, Owen? It's hard when you guys aren't talking and I am. I get it. Here we go. It says, this piecewise function for k of x is below. I have to find the values for a and b. So when I'm done, I'm going to fill in what a is and what b is. They are unknowns right now, and they're in two pieces. They're on a parabola that's in the middle, and they're on a line that's at the end. I need to find the only two, a and b, in the whole world that would make that function continuous everywhere. So the first thing I do is I look and make sure our solid dots, so I'm good. So this is really just forcing the functions to meet and seal up perfectly, which means I have to look at both boundaries. I have to check what happens when x is 2, and I have to check what happens when I make the next transition. I have to force the top and the bottom functions to have the same limits from the left as from the right. So we're going to start with 2. I'm going to go like this. My limit as x approaches 2 from the left, I'm just going to call it k of x. And I'm going to write equals. I'm going to go over here and pretend this was on your worksheet a few days ago. Maybe the one when you were in groups. You would have said in your group, we got to plug it in. Oh crap, we got 0 over 0, but the top factors. Would you have done that? So you would have said, well, right now I'm at 0 over 0, but that just means I've got to figure out where that hole in the graph is. Perfect. So here's what I know. There's a hole in a line, because that plus 2 is a line, and it's at 2. But I need to know how high up it is, because limits are the y values. So what do you think my limit is? What is my limit as x approaches 2 from the left? 4. Exactly. You replug it in, right? Factor, cancel, replug. I'm up at 4. So that first function is a line. It's going at a slope of 1, so about a 40-degree angle. When I hit 2, I have an open dot, but that dot is up at 2, 4. Then a parabola of unknown, right, is going to take off. I need to make sure there's a solid dot. There is. But I need to make sure that that dot's at 4. I love it when I see you guys nodding. So what am I going to do? I'm going to force it. I'm going to say a times, let's do this. Let's write it out nice. Limit, I'm going to write this first batch out nice, and then I'll call it like that. When I approach from the right of the function, when I plug in a 2 for x, my arrow got a little bit pointing at a, this is x, I end up with 2 times 2 is 4, a plus 2b plus 3. What do I have to make sure happens with these two expressions right here? What do I have to force them to be? Equal. So I'm going to write a 4a plus 2b plus 3 better end up being at the same height. And then I think I'll clean it up a little bit and say whatever my a and my b are, I know this has to happen if I subtract the 3. That's as good as that gets. I have one equation, 2 unknowns. Those need to match. If I have 2 unknowns, how many equations do I need? 2. 3 unknowns, guess how many I need? 3. If you get super high levels of math and you have 5 unknowns, how many equations do you need related? 5. All right, so I'm going to go get another one. Right? So I'm going to hop on and make my next transition. My next transition is parabola to another line. It happens at 3. Is there a solid dot? Yes. I'm going to force them to be at the same height. So I'm going to drop the limit notation to speed this up. So basically what I need to do is put in a 3 and a 3. and say 9a plus, I'm going to pretend this is multiple choice, and Caden's issue is speed and accuracy, not notation. Right? Would you agree for multiple choice? If he knows he's taking one, so let's just pretend this is a multiple choice question. So I can drop right now these limits. So I'm coming in from here. I've got 9a plus 3b plus 3. You better be at the same height as this guy, which would be at 6 minus a plus b. I dropped all the limits. I'm pretending it's multiple choice. This looks messy to me, so I think I'll add the a over for 10 of them on the left. I think I'll subtract a b for 2 of them on the left. I'm trying to get it in the same format as this guy. And I get it equal to 3, and that's as good as it gets. But now I have 2 unknowns, 2 equations. So back to Algebra 2, solving a system of equations. You had a whole chapter on it. My system, it's just your a's and your b's were x's and y's, and you were looking for where 2 lines intersect. Now, they're a's and b's, and they're the only coefficients in the world that will cause that guy to not lift its pencil as we travel. Do you remember how to solve that? You're nodding. Good. Somebody last hour said substitution. I said, okay, but that's going to take you 3 times as long as if you just do what? Eliminate. Yeah. I want to get rid of a variable, and as long as I don't do anything illegal, so my choice, I think, is I'm just going to multiply the top 2 by -1. That's legal. Then what do you think I'll do with the 2 that's legal? I'll add them up. Then what? Divide, and I get 8 is 1/3. Done. Up here, for these functions, if I were to go to Desmos and graph these 3 pieces separately, I would have to choose a 1/3 for my A, which means I'd have to do that here as well. How am I going to get the B? How'd you do it in Algebra 2? Almost every problem in calculus, that's algebraic, ends in Algebra 2. Alright? So how do you go back and get the B? Plug the A into the easiest place possible, which would be the top one without the negative. So I'm going to do 4 times 1/3 plus 2b equals 1. And you would solve it, and I'm going to go dot, 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 because I don't teach how to solve multi-step equations. I teach calculus. We're done. Did I make it in under 30? Oh! I got a mission, you guys. To be done in under 30 minutes. So tomorrow we're on the same topic. I made an executive decision to give you all the notes today. So those are long. They were for 2 days. So tomorrow you're going to do delta math. When you finish it, you're going to continue on this. So how long do you think when is this due? This, no. Tomorrow. When's this due to be due? Monday. Delta math will also be due Monday. So if it were me, I would get as far as you can get today. Maybe if you have a study hall or a board tomorrow or in the elk time where you have nothing to do, work on it. Come in tomorrow, work on delta, finish it, and go back to this, and maybe you'll be done and have no homework for the weekend. I wouldn't do homework tonight, is what I'm telling you. Unless you know you have a super busy weekend. But I think between extra time tomorrow, because it's a long hour, it's Friday schedule, plus you have elk times. Tomorrow is not elk times, I lied about that. We had to sign up for an advisory today, so I'm not sure.
I don't like that movie.
You can't search for a teacher.
You can.
You just hit Control F and then
Yeah.